Welcome, everyone. Today, we're taking a look at the fundamental architecture of the universe itself. In this explainer, we're going on a really fascinating journey. We'll be starting all the way down at the unimaginably tiny level of subatomic particles and zooming all the way out to the bulk quantities of matter that we actually interact with every day. Okay, let's dive into this. Here's a quick roadmap of where we're headed. We've got 1. Inside the atom. 2. Elements, ions, and charge. 3. The isotope mix. 4. Chemical formulas explained. 5. Isomers, arrangement matters. And finally, 6. Meet the mole. So, starting with section 1, inside the atom, the scale of the invisible. To really put things in perspective here, the diameter of an entire atom is on the order of 10 to the power of -10 meters. The nucleus inside it, that is about 100,000 times smaller than that. To visualize this, if an atom were somehow magically expanded to the size of a massive football stadium, its nucleus, where almost all of its mass is actually concentrated, would literally be the size of a single tiny blueberry sitting right on the 50-yard line. The rest of that entire stadium, it's pretty much just empty space where the electrons hang out. So let's talk about the cast of characters inside that mostly empty stadium. The nucleus holds the heavy hitters. You've got protons, which carry a positive charge, and neutrons, which are, well, neutral. They both have a mass of roughly 1 atomic mass unit. Out in the vast empty space around them, you have the orbiting electrons. They carry a negative charge, but just look at that mass. It's practically zero. In fact, it would take about 1,800 electrons just to equal the mass of a single proton. Moving on to section 2, elements, ions, and charge. What actually gives an atom its identity? What makes a carbon atom act like carbon, or oxygen behave like oxygen? It honestly all comes down to those heavy little protons. The number of protons is called the atomic number, and that is the defining trait of an element. If you have 6 protons, you are carbon. End of story. Now, in a neutral atom, the number of positive protons perfectly balances the negative electrons. But atoms can easily gain or lose these ultra-lightweight electrons. And when they do, they become electrically charged, which is what we call an ion. Lose an electron, and you get a positively charged cation. Gain an electron, and you become a negatively charged anion. Now, you might be thinking, okay, this is just theoretical subatomic trivia, right? But no, it has massive macroscopic consequences for us. Take the element iodine, for example. Our bodies absolutely require it to produce thyroid hormones. If we don't get enough of this specific atomic arrangement in our diet, it can lead to a goiter, which is a severe enlargement of the thyroid gland. That is exactly why tiny amounts of iodine are routinely added to everyday table salt. It's a microscopic element solving a very real, massive public health issue. All right, section 3, the isotope mix. Same element, different weight. Now, what's really interesting about this slide is that elements often exist as a naturally occurring mixture of variations. We established that protons define the element, but the number of neutrons can actually fluctuate without changing the element's core identity. We call these variations isotopes. Take boron, for instance. In nature, about 80.1% of all boron atoms have 6 neutrons, giving them a mass of 11. We call this boron 11. The remaining 19.9% have only 5 neutrons, making them boron 10. So they're both boron, but they carry slightly different weights. Because of this, when you look at a periodic table, the mass number you see isn't the weight of one single specific atom. It's actually a weighted average. To calculate it, chemists use a pretty straightforward formula. First, identify the exact mass of each isotope. Then, multiply that mass by how common it is in nature, its fractional natural abundance. Finally, you just add those values together. For boron, combining the abundant boron 11 and the less common boron 10 gives us an average atomic mass of about 10.81. Just remember, no single boron atom actually weighs 10.81. It's just the mathematical average of the whole mix. Section 4, chemical formulas explained. Writing the recipes of matter. So to represent these chemical combinations, we use formulas. Take methane, which is CH4. But a simple text abbreviation kind of misses the big picture. When we look at a structural formula, we see lines indicating the actual chemical bonds connecting the 1 carbon and 4 hydrogen atoms. And when we look at a space-filling model, we really see what this looks like in 3D space. The atoms aren't just a random list of ingredients thrown together. They are snapped together in a very specific, physical, geometric arrangement. When we're writing these out, we also need to distinguish between the exact recipe and the simplified ratio. The molecular formula gives you the exact inventory of a single molecule. For blood sugar, glucose, the actual molecule is C6H12O6. That's 6 carbons, 12 hydrogens, 6 oxygens. But if we just want the simplest, lowest common denominator ratio of those elements, we divide by 6 to get the empirical formula, CH2O. So the empirical formula gives us the basic proportion, while the molecular formula is the literal exact building blueprint. Let's look at section 5, isomers. Arrangement matters, when identical ingredients make different things. Here is where chemistry starts to feel a little bit like magic. Let me pose a question to you. If you have the exact same list of atomic ingredients in the exact same quantities, do you always get the exact same substance? I mean, the intuitive answer is yes, right? But the chemical answer is absolutely no. And this brilliantly illustrates why. Consider two completely different substances: acetic acid, which gives vinegar its sharp taste, and methyl formate, which is used to make quick-drying finishes and industrial insecticides. Astonishingly, both of these share the exact same molecular formula, C2H4O2, 2 carbons, 4 hydrogens, 2 oxygens. They are structural isomers. The only difference is how those exact same atoms are arranged and connected to each other. One you'd happily put on a salad, and the other, well, you absolutely do not. It gets even crazier with spatial isomers. Look at the compound carvone. Here, the atoms aren't even connected differently. They are literally just 3D mirror images of each other, much like your left and right hands. S-carvone is found in caraway seeds and smells a lot like rye bread, but its spatial isomer R-carvone smells exactly like spearmint. Just a simple flip in physical space, and our biological receptors interpret them as completely different smells. Arrangement really is everything. Finally, section 6. Meet the mole, bridging the microscopic and macroscopic. Since an atom is mostly empty space and its mass is practically zero, working with single atoms in a physical lab is, well, impossible. We needed a bridge between the microscopic domain and the macroscopic domain, something that links the microscopic properties of atoms to bulk quantities that we can actually scoop out with a spoon or measure in a beaker. This bridge is a specific unit called the mole. It allows modern chemists to connect invisible atomic structures to tangible physical masses, which is a concept known as molar mass. By knowing the molar mass of a specific element or molecule, we can weigh a bulk scoop of a substance and calculate precisely how many atoms are inside. So, the crucial point is this: how do we actually count them? The secret lies in Avogadro's number, a completely mind-bogglingly huge value of 6.022 times 10 to the 23rd power. That is exactly how many atoms or molecules are in a single mole. Just by checking the mass on a scale, chemists use this number to count quintillions of atoms in seconds. So the next time you pour a glass of water, ask yourself, just how many trillions of microscopic molecules are you actually about to drink? Thanks for joining me on this journey from the atom to the bulk. Keep questioning, keep exploring, and I'll see you next time.